The main project of this video is to prove that the derivative of the natural log function is the function y equals 1 over x. So I decided to start by motivating this with an animation. On the left side, we're looking at the function y equals natural log x, and on the right side, we're looking at the function y equals 1 over x. And we notice that the slope values on the natural log function correspond exactly to the y-coordinate values on the function y equals 1 over x. And this is powerful evidence that the derivative of the natural log function is indeed 1 over x. Now, of course, we want to actually prove this fact symbolically, and to get that done, we're going to use implicit differentiation. So the natural log function is an inverse function to a function that we understand much better, the exponential function. And whenever you're dealing with an inverse function, it's really useful to just give it a name. So we're going to say y equals natural log of x. Now this allows us to turn this equation around into an exponential equation. And there we're just using the definition of logarithms. If I have y equals log base e of x, that's exactly the same thing as saying e to the y is equal to x. And this is where implicit differentiation comes in. If I take the x derivative of the left-hand side, the chain rule is going to produce a factor of dy dx, in other words, the derivative, and that's what we're trying to find. So we take the x derivative of the left and right hand sides. Again, on the left side, we have to use the chain rule because y is a function of x, and I'm looking at this expression e to the y. So the chain rule says differentiate with respect to y, that's just e to the y, and then tack on the derivative of y with respect to x. And then on the right hand side, we just have the derivative of x, which reduces to 1. So now our goal is to find dy dx, so we'll go ahead and solve for that. And this gives us dy dx written in terms of y. So we get dy dx equals 1 over e to the y. But now we can replace y with the natural log of x. So we get 1 over e to the natural log of x. But remembering that e to the x and natural log x are inverses of each other, e to the natural log x is just x. So there it is. Dy dx turns out to be 1 over x. And we can write this down as a new derivative rule. d dx of natural log x is equal to 1 over x. So let's wrap things up with a few examples here. In our first example, we're not really doing anything. We're just using our new rule for the derivative of the natural log function. The derivative of natural log x is 1 over x. Now in the second example, we get to combine this with the chain rule. So this is a function composition, natural log of 2x. And the chain rule says differentiate with respect to 2x first. In other words, treating 2x like a single variable. So we start out by saying 1 over 2x. And then the chain rule says we have to tack on the derivative of 2x, but that's just 2. And the 2's cancel here, leaving us with the exact same derivative, 1 over x. And this seems a little bit suspect, like how can the derivative of natural log 2x be the same thing as the derivative of natural log x? We know that replacing x with 2x causes a horizontal compression of the graph. And I'll leave the graphical investigation up to you, but I do want to point out that the natural log of 2x is just the natural log of 2 plus the natural log of x. And looking at it that way, it's unsurprising that the derivative turns out the same. If we take the derivative of this expression, natural log 2 plus natural log x, the derivative of natural log 2 is 0, and it just reduces to the derivative of natural log x, which again gives me 1 over x. In our third example, we have another application of the chain rule. I have a natural log of x squared plus 1. So again, I differentiate with respect to the interior. Treating x squared plus 1 like a single variable for the moment, I get 1 over x squared plus 1. And then the chain rule says we have to tack on the derivative of the argument of the log function, which is a 2x. So it's a little bit nicer if we write that as 2x divided by x squared plus 1. And I want to point out here, because this is so important to recognize in calculus 2 and differential equations and so on, whenever you see the derivative of the denominator sitting in the numerator, you know you're looking at an expression that resulted from differentiating a natural log while using the chain rule. Finally, in example 4, we have the natural log of the cosine of x, so we want the derivative of this guy, and we differentiate with respect to the interior function. So we start with a 1 over cosine x, and then the chain rule says we have to tack on the derivative of the interior function, which is negative sine x. And this one cleans up really nicely. We can write it as the negative of the tangent of x. In the next video, we're going to look at how to extend the derivative of the natural log function to logs with other bases. I'll put a link to that video at the upper left of the end screen, and I'll see you there.